Hi, my name is Julian. I'm a PhD student in the AVS lab at CU Boulder, and today I'm talking about using a pulsed electron beam while sensing electric potentials. So over the last few years, our lab has investigated how to estimate electric potentials of spacecraft remotely with a servicing satellite. And we're working on two methods, and both of them use a electron gun that is equipped on a servicing spacecraft, and the corresponding electron beam is aimed at the target object. The electrons from the electron beam will excite secondary electrons from the target object, and the secondary electrons are accelerated towards the servicing satellite. And by measuring the kinetic energy of those secondary electrons, we can infer the electric potential of the target object if we know the electric potential of our servicing spacecraft. And that is the electron method. The electrons of the electron beam will also excite X-rays from the target object. And by using an X-ray detector on our servicing spacecraft, we can measure the energy of the incoming photons, and that will also give us information about the electric potential of the target object, and that is the X-ray method. I will not go more into detail about these two methods here in this presentation, but there are a lot of papers on our lab website about the electron method and the X-ray method. One of the issues with using an electron beam to excite those secondary electrons and X-rays is that the electron beam might actually charge the target object, but we would like to measure the natural electric potential of the target object. So we would not like to charge the target object while sensing the potential. What we could do is we could change the electron beam parameters, such as the electron beam energy and the current, but we kind of want to avoid that because our remote sensing methods pose some limitations on how much we can change those beam parameters. So we would basically like to choose our own beam parameters and find a way of estimating the potential without changing the potential. And some of the limitations on the electron beam parameters are that the electron method generally prefers a low beam energy because that will result in a lower impact energy, which will give us a higher secondary electron yield, and that gives us a better signal. For the X-ray method, on the other hand, we would like to have a higher beam energy because that way we have a wider energy range of our X-ray spectrum, and that makes it easier for us to estimate the electric potential. And both methods benefit from a high current because that higher beam current will give us a higher signal as well. Really quickly about the charging model that we're using, we're working with we're including a photoelectron current that is generated due to the sun. We also include the plasma currents due to electrons and ions. We have an electron beam current and the secondary electron emission current. So let's look at the effect of a continuous beam on the potential of the target object. So in our analysis, we consider spherical spacecraft, and on this slide specifically, both spacecraft are of equal size, both have a radius of 1 meter. And the graph on the left-hand side shows the equilibrium potential of the target object as a function of the local time of the spacecraft. And the blue line corresponds to the natural electric potential of the spacecraft, which in sunlight is pretty close to zero. And the other colors of the lines correspond to different electron beam currents, and the different line types currents correspond to different KP indices, so different space weather scenarios. What we can see is that even with an electron beam current of 60 microamps, the potential of the target object is affected and will change if you hit it with an electron beam. And the general trend is that the higher your electron beam current, the higher the change in potential, and also the higher the Kp index, the higher the change in potential as well. Now, this is a little bit different if the spacecraft is eclipsed. So in that case, we don't have the photoelectric current, which is a positive current. In that case, the natural potential is pretty, it's not that close to zero anymore. In fact, it's actually the natural potential of the spacecraft, of the target object, is around negative 5,000 volts or so, depending on the Kp index and local time. And even with really small currents of just a few microamps, we actually change the potential of the target object significantly if we emit an electron beam onto the target object. And using a electron beam current, for example, of 10 microamps will change the electric potential from 5,000 volts, which is the natural potential, to down to negative 20,000 volts. Now on this slide, we're investigating the effects of the size of the spacecraft. So on the left-hand side, again, is in sunlight conditions, so including the photoelectron current. And generally, if the target object is really large or the servicing satellite is really small, then we don't have to worry about those charging effects as much, because the change in potential is pretty close to zero, which corresponds to those gray regions here. But if the servicer is large relative to the target object, then the target object will actually charge a lot due to the continuous beam. And in Eclipse, we have a similar scenario with as the target radius increases, we have less charging of the target due to the continuous beam. But the servicer radius would have to be really, really small in order for not to charge the target object. So on this slide, I'm just showing really quickly how what will be the maximum allowed current or electron beam current, such that we don't charge the spacecraft as a function of the relative spacecraft size. So if both spacecrafts are equally sized, which corresponds to the radius, the ratio of the radii is equal to 1, then we could use a beam current up to about 60 microamps and still not charge the target object. However, if the target object is smaller, then we also have to work with a smaller current. Now, in Eclipse, the maximum allowed beam current decreases significantly. So for equally sized spacecraft, we could only use a beam current of about 1 nanoamp, such that we avoid charging. And even if the target object is 4 times the size of the servicing satellite, then we could still only use about 10 nanoamps, such that we don't charge the target object. So that really shows that in Eclipse, we have to worry about charging the object when we work with a continuous beam. And that's really the takeaway message of the last few slides. Charging of the target object while sensing its electric potential is especially a concern if the target object is eclipsed. Now, the target could be eclipsed by either Earth or the Moon, but also by another spacecraft, for example, the servicing spacecraft. So now let's look at the pulsed electron beam. There are 3 types of electron beam pulsing. The first type would be on-off pulsing. So you switch between a 0 and some nominal beam current. In other words, you turn off the beam and turn it back on again periodically. The second type in the middle figure on the bottom is current pulsing, and that in that way you switch between some low current and some high current. And similarly, on the right hand side in the figure is energy pulsing, where you switch between some low energy and some high energy. The control parameters for the pulse beam are the repetition frequency, which basically is the corresponds to the period of your pulsing function, and the duty cycle D, which is the ratio between the time that your beam is turned on over the time your beam is turned off. So here's an example for on-off pulsing. For the entire pulsing analysis, we're looking only at eclipsed target objects. And here on the left-hand side, we see the change in target potential if we're using a continuous beam, so no pulsing. Both the target and the servicer start at their natural potential, and once you turn on the electron beam, the potential of the target object decreases quickly down from negative about 4,000 volts down to negative 18,000 volts. And the potential of your servicing spacecraft increases a little bit. Now, if you use a pulse beam instead, you basically charge a little bit and then you turn off the beam and let the target object recharge to its natural state, kind of. And then you turn on the beam again and turn it off again. And the change in potential is a lot smaller. So we just changed the potential by a couple hundred volts maybe, compared to several thousand volts with a continuous beam. And essentially what this pulse beam does is that it decreases the average current that you use with your electron beam. So for example, if you use a duty cycle of 1%, as in this analysis right here, you essentially decrease the average current to 1% of the nominal current that you're using. Now, you might be wondering why we don't work with just a smaller beam current on the first hand and just don't use a pulse beam at all. And the answer to that is, first of all, your electron gun might not be capable of producing such low beam currents. And the second reason is that using a pulse beam current could actually be better from a signal processing perspective, because if you excite those X-rays and secondary electrons at a specific frequency, you could later on filter out other frequencies in your signal and therefore get a better signal for the one you're producing. Here's just a quick overview of duty cycle versus repetition frequency. So the duty cycle affects the change in potential of the target object. But so for example, if we use a duty cycle of 1%, we'll change the potential more than if we use a duty cycle of 0.2%, for example. And the repetition frequency affects the amplitude of those oscillations due to pulsing, as we can see on the right-hand side. So similarly to those figures we saw for the continuous beam, I'm looking at the change in potential of the target object over local time for different KP indices on the left-hand side. And generally, in eclipse, the potential will change by about 15,000 volts if you use a continuous beam across all local times. But if you use on-off pulsing with a nominal beam current of 10 microamps, you can actually decrease that effect. So with a duty cycle of 0.1%, for example, you barely change the potential of the target object. And even with a duty cycle of 1%, we still change it only by a few hundred volts compared to several thousand volts with a continuous beam. Now on the left-hand side, we see what maximum duty cycle we could use such that we change the potential by 100 volts or less. And basically, it's very similar to the maximum allowed current. If we have equally sized spacecraft, we could use a duty cycle of about 1%. But if the target object is bigger than the servicing satellite, then we could even go up to about 10% for a duty cycle. And on the right-hand side, similarly, the maximum allowed duty cycle over local time. So this is also a function of local time due to the different charging scenarios. In conclusion, we saw that the potential of the target object is affected while the potential is being sensed with an electron beam, with a continuous electron specifically. And that change in potential is even more drastic if the spacecraft or the target object is eclipsed by either the Earth, the Moon, or another spacecraft. And we can use a pulsed electron beam to reduce that effect and to reduce charging. Feel free to reach out to me with any questions, either per email, on LinkedIn, or by visiting our lab website. Thank you.